Just before we dive into Amy's housing, I should mention one thing. Before the weekend, I sent you all a note saying if you've left your machines on, please switch them off because you'll end up using up all your free credits on a machine that you're not even using. Well, guess what? I forgot to switch it off myself. Unbelievable. So I logged in this morning, and not necessarily because I left it switched on just over this weekend, but so far I've used about 5% of my free credits, which is more than I wanted to by this stage of the course, albeit that I've been going for a good few weeks longer than you have, trying to get this whole thing set up. I'm quite tempted, in any case, well, firstly, I'm going to try and be more careful in future and turn the machine off when I'm not using it. Secondly, I'm actually quite tempted to release my static IP just to try and save a little bit on those ongoing costs. That would mean that the only thing I'm paying for when the machine is not running is simply the 30 gig hard disk, which really costs from memory a few cents per month, so maybe $1 per month. The other thing is, you must have caught me at a really good mood when I released this student version to you on Moodle, because I can see there's hardly anything for you guys to do other than click through it and answer a few questions. In particular, I didn't ask you to program up K-fold cross-validation yourselves. That's probably a bit of an omission because I normally find that people only really understand things when they code it up themselves. Be that as it may, if it doesn't quite make sense, please, as I always say, ask a question on Moodle and we can discuss it in our weekly catch-ups. Here goes. Notice we are going to import something called lasso CV, which unsurprisingly, the CV bit stands for cross-validation. The same loss functions that we used previously for ridge regression on Amy's housing we're now using for the lasso. Input the data, and we've seen previously how we split the non-test data into train and val. In this particular case, we're just going to feed into lasso CV all the non-test data, and itself will split that data into train and val using 10 different folds. So it will carry out the train validation process 10 times, each using a different tenth of the data. You can notice over here that I've done the standardization manually, simply deducting the mean of each feature from the feature. The code isn't so obvious, but have a think, you should be able to figure out what that's doing. And likewise, then dividing each feature by its variance. Best not run that again, or it might do something funny. And finally, as you can see, we're splitting simply into test data and non-test data. To do, what is K-fold cross-validation? Well, you know what K-fold cross-validation is because we talked about it. When is it better than the simple train validation split we used previously? Well, that's a strange question. Always? I don't know. Not sure why I ask that. I suppose if we had loads of validation data, then there wouldn't be any need to do it, and it would just be a waste of time. 10 lots of lasso regression. Whilst it works really quickly on this data, and some of the data sets that I use, doing even one fold of lasso or ridge regression can take 2 or 3 hours. That being said, even when I'm doing it, I'm using a machine with 40 cores, and it can run a separate cross-validation on each core. So even in that case, there isn't a massive cost of doing K-fold cross-validation. So I'm not sure what I meant by that question when I wrote it. What is the optimal value for K? Well, again, I'm not sure why I asked that. Typically people use 10. If I'm short of time and short of compute power, I might only use 3 times. And I guess if I really wanted to know what the optimal value for K is, I would turn K into a hyperparameter and figure it out just like the way I would tune any other parameter. Maybe that's what I was getting at, that if you have to make decisions in machine learning, you can simply turn that decision into a hyperparameter and then use K-fold cross-validation on that. I'm looking at what I wrote here. Below alpha is the regularization strength. Well, if I'm looking here, there is no parameter alpha. So I think for your version, I'm going to delete this and then have a quick look at what actually is going on in lasso CV. Lasso linear model with iterative fitting along a regularization path. The best model is selected by cross-validation. The optimization objective, which we call the loss function, is 1 over 2 times the number of samples, y minus xw squared. Oh, XW, this is the error, this is all of the errors, and this is a LaTeX way of writing the L2 norm squared, which is kind of what we would expect. There's just a little 2 over there which wasn't in any of our work. I probably just omitted it. It makes no difference to the final predictions. It would actually make a difference to lambda, which if you remember here they've called alpha, and as you can see the penalty is the L1 norm. But I'm curious as to how we are going to find alpha here, because we haven't given a regularization path. I can see it's going to go through 100 alphas, but how is it going to choose them? Interesting. So you either give it the regularization path itself, like we did when we set lambda previously when we were doing ridge regression 1, 2, 4, 8, 16 and so forth, but it seems here that it will choose for us which path it's going to try. I can't see how it's chosen that path, but we're going to trust it to choose a good path, and we're going to run it. Inspect the coefficients. Is the intercept penalized? Well, the intercept is pretty big. It shouldn't be penalized. I guess one way of checking whether the intercept is penalized or not is to check whether the average of the predictions on train is the same as the mean of the target variable on train. I would just say no, it's not penalized. How many non-zero coefficients are there? I can't believe I did this all for you. I wonder if I just filled it in last year and then forgot to remove it. Never mind. The coefficients are given by a data frame, which we will create. But over here, we're extracting the coefficients. And now I'm really puzzled. Why would I round the coefficients to 0 decimal places? It seems such a puzzling thing to do. I'm going to remove that. Let's just break that out a little bit to see what's going on, because it is a bit of a puzzle. Let's have a look at these coefficients. Well, you can see there are some which are exactly 0, so I'm puzzled as to why I ever thought I needed to round them to find the non-zero ones. And on the contrary, I wanted to demonstrate that they do get set to exactly 0 and not 1 times e to the minus 15, or whatever it was when we did ridge regression. Puzzling. We're going to find the coefficients. The coefficients matrix, or the coefficients have how many rows? Oh, I don't know how many rows, sorry, I was looking at the head there and wondering why I could only see 5 rows. 216. That is exactly as many independent variables that we had. So that bit is not surprising, and at least it's correct. Now we're going to take only those coefficients that are non-zero. That's good. Even without doing the stupid rounding thing that I was doing before, we have gone down from 216 coefficients to 155 non-zero coefficients. I'll just run the rest of the code here. I'm adding the sign of the coefficient, and I'm taking the absolute value of it as well, so that I can sort by the absolute value. So we can see the largest coefficients. Well, I kind of feel that this model makes a good bit of sense. One thing we need to remember when looking at these coefficients is that they are based on the normalized data. So the variance of each column is 1, as is the standard deviation. So when we have a coefficient over here, it means that a property which has I think this means ground floor living area, 1 standard deviation bigger than average, will cost $28,000 more than average. It might have been preferable to get these coefficients in terms of the original scale of our variables rather than the standardized scale of our variables, and that's what sensible penalized regression models do. They will normalize your data in some way, but when they return the coefficients, you'll get them on the scale of the original data. But anyway, it does seem to make sense that the living area, the overall quality, the year built, the basement square footage should make positive impacts on price, and maybe